Imagine that you're trying to learn how to ride a bike. You practice for multiple days, but you keep falling and make almost no progress. Then imagine that something clicks in your head, and all of a sudden you're able to ride smoothly without falling. This transition from not being able to do a task for a long time to being able to do it perfectly is exactly what happens when we train neural networks. When training transformer models, which are the neural networks that power modern AI systems, they often get completely stuck during learning. The model will train for thousands of steps with barely any improvement in its loss, which is how we measure how well the model is learning. This is called a loss plateau, and it wastes huge amounts of computational resources and time. There's also another very similar phenomenon to this called grokking, which is when you train a neural network and it's able to reach perfect training accuracy by basically just memorizing the answers of the training data set, but it has a test accuracy of almost zero, meaning it can't generalize to other unseen data. But after training for a long period of time, all of a sudden is able to generalize perfectly, reaching perfect test accuracy. And this is what's called grokking. Now, these plateaus are a problem because it makes the training process unpredictable and inefficient because it leaves you wondering when or even if your model will actually learn to generalize properly. Training large AI models is incredibly expensive, costing millions of dollars and consuming enormous amounts of energy. So, being able to reduce the time needed to train could save this money and energy. So far, researchers have actually been able to shorten this loss plateau through various methods. One of these methods is ratio tuning, which is where you intentionally flood the training data with examples so that you can force the model to learn the general rule. And another method is grok fast, which is where you use a filter to favor updates associated with generalization over updates associated with memorization. But the problem with these methods is that they're limited by scalability, computational costs, and memory overhead. So our project aims to answer this question: how can we shorten the loss plateau while also maintaining a robust model with good performance? So we plan to implement several strategies to try to achieve faster generalization using fewer training steps and see how they can overcome limitations that others have faced in the past. Some things we plan on doing are incorporating task diversity, using different model architectures, as well as using different model parameters like initialization and regularization.